All right. So, yeah, go ahead and share anytime. This must be a Physics 121 question, right?
Yes, it is.
Mm-hmm.
Right there.
Oh, nice one here. So a skateboarder rolls down a curved ramp, radius 3.85 meters. At some instant, he is traveling with a speed. So let me write down radius and speed 3.06 meters per second. Oh, and his speed is increasing. Oh, okay. Now, I'm going to talk about this a little bit, that because the centripetal ones get kind of challenging.
Mm-hmm.
Maybe you've already noticed that, right?
I've definitely noticed the challenge part. Yeah.
Meters per second. Okay, and now the angle between the acceleration. Okay, so between the acceleration and the velocity, is theta. Okay, so it doesn't say what theta is. Oh, and that's probably the question, right? Find theta?
Yeah. Yes, that is the question.
Nice, nice. Okay, good. Well, since my camera's not working, I'm gonna now that I wrote down the question, I'm gonna switch over to the whiteboard here.
All right. Yeah, I was wondering why you weren't recording the way you normally do.
Yeah, I couldn't get my phone to hook up, and I'm kind of having fun writing on my screen, so that's been kind of fun. But I don't know if it's quite as effective because the writing looks kind of scribbly.
Yeah, I think it's just as effective. It's working well.
But yeah, maybe right. Maybe that's not too important. Okay, but anyways, let me switch over. Let me see. Find the whiteboard. There it is. Let me share. Okay, so let me move this stuff up. This was must have been at the last break there. Okay, now I'm going to kind of review or maybe teach you for the first time. I don't know, but here's the idea of things going in a circle. Okay, let me see. Let me check. I got my black marker going. Okay. All right. So here is going to be my circle. No, that's not a circle. Let's try again. There we go. There's a circle.
Mm-hmm.
All right. Well, that's not a very good circle. Yeah. See, I struggle writing on the screen, but you can see that, right?
Yes, I see the circle.
Okay. So let me make a point somewhere on the circle. And let's pretend this object's going around the circle. Okay. Its velocity at that instant would be like this, tangential to the circle. Okay. Then there would be, and how best to describe this? I'll draw this. This is the radial direction. There could be an acceleration that would be, and maybe I'll change colors to blue, maybe in this direction. But here's a key to the ones that always go in a circle. This velocity vector here, you're going to want to think about as made up of a component that is in the radial direction and a component that is tangential. Okay? In previous parts of this class, when you've been doing two-dimensional motion, you thought of it as X and Y.
Mm-hmm.
And we don't like to call it X and Y because, later on, the object is here. And so its velocity vector would be this way. And maybe its acceleration vector would still be this way. And so you would want to break it apart. So if this is the radius at that point, you would want to break it apart into how much is radial and how much is tangential. So my suggestion for students when they're doing problems in 2 dimensions is always make a grid. And if this was projectile motion or something like that, I would say make 1 column X and 1 column Y. But for this problem, let me erase the X and erase the Y. And let me put R for radial direction and T for tangential direction. And coming back to this picture, this piece right here is the radial direction. And this piece is the tangential direction. And the lesson from the lecture or the book was and is this, that the acceleration in the radial direction is always going to equal v squared over r. That's the part that makes the object turn. The other piece, the tangential piece, is related to the change in the speed. And then the time taken for that change. Okay? And they gave us those. Watch, I'll continue on with this calculation. So the problem said that its speed was 3.06 meters per second. Its radius was 3.85. So the first calculation I would do would be to this, 3.06 meters per second squared. And the radius is 3.85 meters. I'll look at the units first. This meters squared and a meters down there at the bottom would make only 1 meters in the top, but I'd still have a meters squared. So that's the appropriate unit for acceleration, meters per second squared. And then grabbing my calculator, 3.06 squared divided by 3.85 comes out to be 2.43 meters per second. So that would be, if I come back up to this picture, this component here. Now let's look at the tangential component.
Wait, sorry, I didn't see which component.
Oh, right here, right there.
Okay.
And I'm gonna redraw that picture in a second once I do these calculations.
Okay.
And I'll draw a new picture. Let's do this calculation too. So the change in speed and also the time taken is what they gave as the 2.1 meters per second each second, which I think in the problem wrote it as 2.1 meters per second squared. And so maybe I should have said there's really not a calculation here. This really means the rate of change of speed. What rate is your speed changing? And so we know that number. So if I kind of redraw that picture, I guess it would look something like this now. Here's the circle. Here's maybe the little blob that's going off in this way. That would be the velocity vector. And what we just found is the acceleration vector. We found, and I was doing it in blue before, so I'll do it again. We found something that's going off like this. And the components, which I did in red, would be this component, which would be the radial component, and this component, which would be the tangential. So this first calculation is the 2.43. That's this component, the radial component. The tangential component is the 2.1. The question is asking for this angle right here, theta, which there's a couple ways we could go from here, but maybe I'll just say that's the same as that angle.
Okay. Yeah.
So if I say tangent of theta is equal to opposite 2.43 over the adjacent 2.1. And I grab my calculator, start with 2.43 and divide it by 2.1. And let me just check if my calculator's in degrees. Okay, it is. So then if I go inverse tangents of that number, I get 49.2 degrees. And,
Hey, yeah, I see how you got that. Yeah, I wouldn't know that saying that its speed is increasing at a rate of 2.1 meters per second squared. I guess, I mean, it makes sense now that you showed me that.
Well, fair enough. And that's actually, I mean, what you just said is very, very common. And it's really actually, as you pointed out, very, very simple. But for some reason, when students first hit this chapter, they don't connect that the tangential piece is the rate of change. And so when they just say it's 2.1, they've already given you that component. And so I would say the lesson to learn here is to know that, okay, the acceleration, like any vector, can be listed in parts. And my recommendation for you 121 people here is, just like we would do X and Y for projectile motion, anytime you have circular motion, you want to break it into its two pieces, which we call radial and tangential.
And it would always be the case that your radial acceleration is v squared over your radius.
Yeah, exactly. Yeah.
Okay.
Yeah, v squared over r gives you the radial one. And the tangential one is how your speed is changing. So that could be, a big number, a small number. It could have been a negative number, could have been slowing down.
Okay, that makes sense. Thank you.
Oh, in fact, maybe I should have read it. Sometimes if I wasn't careful reading it, it could have said it was slowing down at 2.1.
Speed is increasing.
So. Okay. Yeah.
Yeah. It says speed is increasing. So.
Okay. Yeah. That's how I interpreted it. Okay.
Mm-hmm.
Good.
Thank you.
Good. You bet. Here, let me. I'll turn off that share so I can come back here. Okay. Well, I saw Claire had popped in, and she didn't leave a question. I wanted to. All right, but I shall move on. Looks like Anthony, you got a question here, number 47. Okay, I'm gonna actually write that down here. 122. I'm going to assume that's chapter 26.
Yeah.
Everybody's been asking about 26. Well, that makes sense. That's good. I mean, people are actually doing very well. If you're working in 26, it's kind of the plan. You're that good. I mean, you're on the plan.
So next week is 27, and then the following week is 28 and the test?
I'll say yes to that, but if we keep doing a chapter a week, that's a little too fast for our pace.
Oh.
So
Okay.
I would say, since your test is only chapters 23 through 26, you might be better off to make sure next week that you understand the material for the test before you move into 27.
Mhm.
That's what I'm going to recommend when I communicate with you on Sunday night for the week. I'll say, okay, now, all right, you can start chapter 27 and nothing's wrong with that, but more important than starting 27 is getting yourself ready for the test, because 27 is not on the test.
Yeah, and there's a bunch of, are there videos from like the review sessions from previous years?
Yes.
Yeah.
And I'll share those with you on Sunday. I think I was sharing that with Daniel earlier in one of the sessions that I have a couple of videos you could see. I did a review session and recorded it for this class, probably about 3 years ago, maybe 2 years ago, where I just took a bunch of problems from old tests and just went through them. So what I'm going to do is Sunday night, I'm going to send that to you.
Yeah.
And I'm going to recommend
we can do the problems from those old tests.
Yeah.
We're in good shape.
Yeah. Try those first, and then watch my review. And then you could also, if you look ahead in the video lectures, whatever year I video recorded these, which I think it's 2013.
Yeah, 2013.
Yeah. If you look ahead, you'll see that after the students took the first test, I went over the test in class. So you can go over that test too. And so I recommend you do that before the test, not after the test. Yeah. And so
there's 3 total tests in the final, right?
Correct. 3 total tests in the final. Yeah. Right.
Yeah. So it's about 4 chapters per test.
Yeah. Every time it's 4 chapters. We do 4 chapters a test, and then 4 chapters a test.
If you do a chapter a week, you finish what, 3-4 weeks early?
Oh, right. And that's why I was saying is we really have, for every test, we have 4 chapters, but we have 5 weeks to get ready for it.
Okay.
So we have a little bit of a chance to kind of let things sink in. So, like I said, the test is still on the 29th, so it's still 11 days away. And you're doing 26 now, and 27 will not be on the test. So this is the time for it to sink in. You're probably still feeling like, I don't get this. It's really not solid with me, and that's fine as long as you're working on it. That's a good place to be. Is that you're not behind. You're just not solid on it yet. But hopefully in 11 days you'll be solid. That's
How's it going to work with DSPS? Just get double time?
Yeah. So I'll go through I got all that paperwork on you guys in DSPS. And so when I schedule the test, make sure I did the timing right. And I could make a mistake, but I think I've got that part figured out. There's a lot of other things about this online teaching I haven't got figured out, but that one I got figured out. I'll just, because the first thing I do is I just set the time for everybody, and then I get the DSPS chart, and then I go through that, and I said, okay, this person gets a time and a half, or this person gets double time, or this person gets whatever, and then I can just change the setting individual by individual.
Cool. Sounds good.
Yeah. In the same way that I don't know if I've done it for you guys, but I've done it for a number of people that for whatever reason they said, oh, I meant to turn in the lab and I didn't, and now it's closed, or there's a lot of reasons. I had one student who their living situation is a mess, and so they're trying to find a new place to live. So I said, look, that's fine. I'll just I can go in and individually change your due date on the lab. So
what is the how strict is the grading on the lab going to be?
Oh, no, not at all. The lab and the homework are about the same.
Yeah, because I've been putting a lot of like effort into those labs, but then I look at it afterwards and I'm like, I don't know if I have it all here, but
No, yeah, and I probably should give you some feedback on those labs. And see, you've turned in what, 2 of them so far? This is the third one?
3.
3, and I just turned in the 4th one.
Okay.
I'm gonna turn in the 4th one
But
tomorrow.
if you'll get full credit if you did the lab, it's part of the learning process. So
Okay.
homeworks and labs, you should be getting full credit. If you did it, you get full credit.
All right.
Okay, so it's more homeworks and labs are just more effort, whereas the tests are the main points.
Right. Exactly. Right. So and that's why I was saying to somebody last week, it might have been you guys, but I'll say it again, that to get, say, 90% in the class, you don't need to get 90% on the test. You need to get 86% and do all the homeworks and labs. Because if you do all the homeworks and labs, plus you get 86% on the test.
And that's the just average, right? So you could get like a couple of 90s, 170.
Right.
Okay.
Right. And so to get a B in the class, which is 80%, it doesn't mean you have to get 80% on the test. You only have to get 73% on the test. And then when you factor in that you did all your homeworks and your labs, you'll get 80%.
Mm-hmm. And is this grade curved like 121?
He curved it in 121?
Yeah, he did.
I always keep in the back of my mind that I might curve it, but I've done this long enough that those come out to be pretty good. There'll be some curving.
Yeah, they should be pretty even.
But those people who, I'll just say, deserve a B, usually score like 75, 77 on the test. And then they do all the homework and labs. And then when you calculate that, it comes out to be 82 overall. And it, works well. Yeah.
Right. Okay.
But, but I always look at it and sometimes I go, oh, I got carried away on that test or something.
Mm-hmm.
And I'll go on to your question, but Elizabeth, you look like you wanted to ask a question or just wanted to say hi. And
yeah, I mean, I just haven't gotten a chance to come in and like introduce myself, and like the test totally like creeped up. It's next week. So I was like, I could like pop in. Yeah. And then I also just like am curious about taking the test. Like how does that look? Like,
yeah. And telling you and everybody else, I'm going to, since the test is coming up Sunday, I'll have a lot of information about the exam, but it'll simply be I'll set the window in Canvas, and you'll have to take it within that window. And I'll even say, if anybody can't make that window, let me know. I can give you a different window. But for most of you, it'll be that window, and I'll give you. Let me just double check. You're in the 101. I recognize your name.
102, but yeah.
Sorry, that's what I meant to say. I don't have a 101. 102. So you guys in the 102 would have an hour and 20 for the test, and I usually just add an extra half hour for this whole learning environment, giving you a chance to scan it and do that. So that would make an hour 50.
All right, that sounds cool. And then, yeah, okay. And then I asked the question earlier. It was just like a little question about like I haven't gotten a chance to go over all my homeworks, but for the chapter 1, exercise 2, you did 36.25 days, like when converting a year to seconds. And I was just confused as like, why 0.25? And then someone said it was like because of the leap year.
Oh yeah, that's where I saw your name. Yeah. Somebody answered you on the chat, and then you were gone later on. We had a fun discussion on that after you had left. But that's exactly it. It was on it. Right. And let me point this out too, because that always confuses them. you would have gotten full credit on the test if you put 365 versus 365.25.
Okay.
That was not the whole reason for that one.
Right. Just like being able to do it. Yeah.
So 365.25 is just a little more accurate, but it doesn't. If somebody puts 365, it tells me they know what's going on and their thinking is there and they deserve full credit. Yeah.
Right. So is that how your test, like, you grade, like, based on, like, I mean, obviously accuracy is part of it too, but like you do, like, it's not all or nothing. It's like,
Right. For your class, there'll be two parts. There'll be the first half will be multiple choice.
okay.
So that one is, it's either right or not right.
Right.
And then the second half are these short answers where you'll be asked to do a calculation.
Mm-hmm.
And I will mostly look for logic. So if your logic is good, but something kind of minor, especially at the beginning, it can look on the surface like it's totally wrong, but I know what the student is thinking. And I go, well, their thinking is almost dead on.
Right.
They just made a little mistake at the beginning.
Okay.
And so I usually, for your class, I grade it on a 3-point scale, and it kind of goes this way. If you do everything completely right, you get a 3. So there'll be 10 of those problems, okay? So you'll get, assuming you do every 10 of them right for 3 points each, that would be 30 points for the fill-in, okay? Or I guess you might call it free response questions, okay?
Right.
Now, then if you just did something really, really minor, like didn't write down the units at the end, or put a minus instead of a plus, those I tend to just take a half a point off. So you get 2.5 out of 3. But my thinking is usually this way. A 2 is where the problem is mostly right. There's just a little wrong. So I call it more right than wrong. And then a 1 is where, okay, there's some stuff here that's good, but it's more wrong than right.
Right.
And a 0 is kind of obvious.
Yeah.
And the 1.5, sometimes I grade a 1.5 because there's a number of problems that have like 2 steps. You got to do this first and then the second step. And sometimes students will do the first step completely right and just stop.
Right.
And
Like net force.
yeah. They just stop. So I think, okay, well, I guess that's worth 1.5. They did half the problem. They did it completely right. I don't know why they stopped, but they did.
Right. All right. Cool.
Yeah, so I need to start working carefully with you guys because you guys have a test coming up next week, and
Right.
You're going to start being nervous about it. So I'll
Right.
start communicating more with you. And the other class, I'll start communicating with you because you guys too are going to start getting nervous, but yours is the following week. So get a little more time for 122 people.
A little bit more time before we get stressed out.
Yeah. No stress, hopefully, but I don't know.
It's hard to believe that the semester's already a fourth over.
Oh, I know. I feel like I'm still getting started. I'm like, wait. How can we be already at the first test?
It's so crazy.
Yeah.
It's weird. Online is so different. It's crazy. But yeah. Well, thank you for that. I'll
My
stick
pleasure.
around a little bit, but might head out. So
Yeah, I don't feel obligated in either way. So, this is all designed to help people who have questions. And so some people come, some people don't. Some people come with one question. Some people hang out for a long time. So I don't want to consume your time if you don't need it. It's just for your benefit.
okay.
All right. All right. Sorry for that delay there, Daniel. I'll finally get to your question here. All right. So back to what was it? 47.
Yeah, it's Anthony's question.
Oh, Anthony. Okay.
Yes.
My question is after his.
Okay. Anthony. All right. So let me jump over to the questions and scroll down to 47. 47. That's 50. Oh, okay. This says 4 parallel metal plates, P1. Oh, they got a nice little picture. P2, P3, and P4. Each have an area of 7.5 square centimeters, and they are separated by a distance of. And so let me write some of those numbers down, so when I switch back over and start doing the whiteboard, you guys, I don't have to leave here. So D is 1.19 millimeters, and the area is 7.5 square centimeters. It's connected to a negative of a battery at P2, and it's connected. Okay. Oh, I see here. Oh, this is going to get interesting. I better copy this picture over too. All right. Let me read that again here. Okay. Each has an area separated by successive distances of 1.19 millimeter as shown in the picture. P1 is connected to the negative terminal. Okay, I see that. P2 is connected to the positive. The battery maintains a voltage of 12 volts. If P3 is connected to the negative, what is the capacitance of the 3-plate systems, P1, P2, and P3? Oh, okay, I get that. And then B, what is the charge on P2? C says if P4 is now connected to the positive terminal, what is the capacitance of the 4-plate system? All right, I might have to come back and forth to that. In fact, maybe I will do this. I haven't done this yet today, but before I go to my whiteboard, and why you guys, I think, can still hear me talk, maybe I will copy that image from the book if I can get to the questions. Oh, here we go. And it looks like I'm getting close to 47. Yeah, here we go. All right. I'm going to bring this whole, I might as well bring the question as long as I'm getting the picture here. What is, how do we copy this? Oh, good. There it is. Copy. All right. So let me come back to the Zoom. Uh-oh. Where'd the Zoom go? Okay, there's my Zoom. All right, come back to the Zoom. Now I'm going to share my whiteboard so we can all join this together. All right. All right, and this was Anthony, right? All right. So let me move this up. We just got done with that one here. Let me put my little cursor here, and let me go control paste. Okay. Maybe I didn't do that right. Let me come back. I thought it said it copied it to my clipboard. Try it again. I heard the beep, but I didn't see the little, okay, now I see it. That's much better. Okay, let me come back to the whiteboard here and control paste. Hey, be nice to me. Oh, wait a minute. Is that it?
Look at that. There it is.
Oh, that was crazy. Maybe okay. Since I've been doing so much handwriting, I guess I don't really know how much I was zoomed in or zoomed out. Wow. Oh, you know what? That would make sense because when I was doing this, I was seeing small numbers like 5% or something. So what would happen if I went to that writing? Would it be like gigantic now?
I think it would take an hour to get there.
Okay, so let's not do it. All right. All right, so let me just work there. Okay, so here's here's the diagram here. I'm going to make it a little bigger here Because what I want you to kind of see in this is if I draw this in orange, the P2 right here is going to get positively charged, and the P1 is going to get negatively charged. And that right there would make a capacitance between P1 and P2. So I'll kind of color that in. Oh, but now I lost the negative there. But then if you use this little switch right here at the bottom and connected it, that would also be making this negative. And if I can draw right below it then, this is how I would be viewing it. I would have a that is a fat line. Let's see if I can erase the fat line. Okay. Let me try this again. All right, so I'll draw a 1 line, 2 lines, and 3 lines. Okay, and so if this is supposed to be P1, and this is supposed to be P2, and this is supposed to be P3, and there's a negative on here, that would make a positive on this side of the metal. But as we charged up this P3 negative, there would be an equal positive formed on the other side of P3. So the electric field from P2 to P1 would look like this, but at the same time, there would be a field here.
So is P3 not going to have any effect on the field towards P1?
Correct.
Okay.
Correct. And that's what makes the problem
Doable.
both challenging and doable, is that then you could view this to look something like this. That what I have is a battery, and the battery has one capacitor with the positive here at P2 and the negative at P1. But also then a second capacitor is in parallel with the first one, where this negative here is P3, and then this is actually the other side of P2. And now what looked like a harder problem is, well, I'll just say easier. I don't know if I'd say easy yet, but it's an easier problem now that I have these two in parallel. Because coming over to here, the part A says if P3 is connected to the negative plate, what is the capacitance of the 3-plate capacitor system?
But now it's just 2 capacitors in
Right.
parallel.
Right. So it would be take the capacitance of the first one and add it to the capacitance of the second. And since they're identical, they would be just twice one of them. And since they're parallel plate capacitors, it would be 2 times epsilon naught times the area over D. And this would then be 2 times 8.85 times 10 to the negative 12. The area I wrote down as 7.5. I'll got to be a little careful with our units. They say square centimeters. So that'd be 10 to the minus 4. And then the separation distance is the 1.19, and they say milli, so that'd be 10 to the minus 3. So then, grabbing a calculator, 2 times 8.85 times 10 to the negative 12. 7.5 times 10 to the negative 4. 1.19 times 10 to the negative 3. And so the two of them together is 1.1. I'll round it to a 2. Times 10 to the negative 11 farads. And I think that was part of A, but there might have been more to it. Let's see. Let me come back to the question. Part A, if P1 is connected to the negative, what is the capacitance of the 3? So I did that. And then B, what is the charge on P2? So P2, coming back to this picture, is actually the sum of the charges really on both of them when I draw it in this way. Or another way of saying the same thing, it's double the charge on one of them. So if I say, okay, so B says that the charge is the capacitance times the voltage. I'll use the whole capacitance, 1.12 times 10 to the negative 11, or the whole capacitance. And then the voltage is the 12 volts. So that first number is already in my calculator, so I'll just go times 12 volts. And so this would be the 1 point, it's like a 3-4, times 10 to the negative 10th coulombs. And again, notice I used the total capacitance because that's going to be the total charge on P2. P2 has got both of them both of them involved. If I come back to the question, then it says now what? And so if P4 is now connected to the positive terminal, right? So back coming at this picture, I would say, okay, so now if we did this and it had a P4, which we now charged positive, P3 would kind of behave like P2 did, where there would be negatives on both sides.
Is it going to be like just another capacitor in parallel?
Yeah.
Okay.
And so it's exactly what you're supposed to recognize. That now this is the equivalent of 3 capacitors in parallel.
Yeah. And you just got to, now it's just 3 times C1.
Yes, good. Well put.
Okay.
Now be careful with D though. What's the charge? The charge on P4 is only going to be the charge on one of those 3 capacitors. Not.
Oh, yeah. Yeah. It's because it's not, P2 is 2, it has 2 adjacent, right?
Yeah.
Yeah.
Mm-hmm.
Okay.
So P4, I guess to kind of do the number quickly, I would say that P4 is going to be half of what I got before right there, half of that one.
Yeah.
All right. Sounds like you got it. I'll go on. Should I check the solutions or did that seem right?
I can check them.
See if I did it right. In fact, maybe I'll go D would then be half of that. So if I divide that by 2, that's 6.6.
2 picofarads. 134.
minus 11 would be the coulombs. And then C, as you said, would be 3 times C1. Although it looks like this number here, 1.12, was 2 of them. So I'll divide it in half and then multiply it by 3. So is this a 1.68 times 10 to the negative 11?
Yeah, that looks, I think that's it.
Yeah. Okay. Good. Good. But yeah, I mean, it sounded to me like, yeah, it wasn't so much the calculations for you, but it was more of it's to recognize a stack of plates like that is really acting like a bunch of capacitors in parallel. That's hard to see. Yeah.
Okay.
All right.
Thanks.
Nice. All right. I'll stop the share there and say, all right, I think with Daniel, you were next here. Okay. When done with Anthony's question, can we do, and yes, we can, or at least I can try here. I'm going to write it down so I will add that to the video links when I send them out. So chapter 26, number 6. Good. Okay, so actually, I kind of like copying the question. That was kind of cool. I might do that more. Let me scroll up to number 6 now, or at least, well, I'll do it today. When I get my camera working again, I don't know if I keep that. I like what I was doing here. Oh, excellent question. This is really the same question, Daniel. Yeah, this is a multiple plate capacitor also.
Yeah,
But,
I was just having trouble picturing it, I guess, or picturing what to do for it. So
Yeah. Okay, well, okay, that's fine. I'm gonna run through the same thing that I was just doing here in the last problem. Let me come up to here and say, all right, if anybody wants to be scanning through the video real quickly, I'll do this so they can see. It's number 26, number 6. And I think if I do a paste, it'll just show up. Good. Let's make that a little bigger though. Maybe that's too big. How about right there? Yeah, I like that. Okay, so here it says, oh, and I'm still sharing, aren't I? Did I turn that off?
yeah, you turned sharing off.
All right, my bad. Because if I do it, oh, I guess I have to because I need to come back to the, anyway, sharing. So turn the sharing back on. I got the question on there, whiteboard right here. Oh, that's the wrong whiteboard. I like this whiteboard. Okay, other whiteboard. Here we go. All right, so here it says a variable air capacitor is used as a radio tuning circuit and is made with N semicircle plates, each of radius R, and positioned a distance D from its neighbors. So no numbers really to work with. To which the electrical connections are shown in figure 2616 and in P26.6. A second identical plate is intermeshed with the first set. Okay. Each plate in the second one is halfway between the first set. The second set can rotate as a unit. Determine the capacitance as a function of the angle of rotation, where theta equals to 0 corresponds to the maximum capacitance. All right, let me try to draw on this picture. I'm gonna make it a little bigger and see if my drawing will help here. But what I'm trying to get you to see, maybe I'll do it on the side here, is I would have a plate and another plate and another plate and another plate. Those aren't very straight lines. But if you were to say this plate right here is that one, and this plate right here is that one, then the one that meshes together, this one would be here, and this one would be here. That's a ugly looking picture.
So is it like you're taking two
But
two things and kind of mashing them together?
yeah, so it would be like if this was the bottom, a plate, a plate, a plate, a plate. That top half one is coming in between them, down to here, down to here, down to here.
Okay.
And when you charge it up, this one might get, say, positively charged, and this side would be negative. This side would get negative, and this side would get positive. This side would get positive, and this side would be negative. This would be negative, this would be positive. And so, like the one we just did, I think the author had a better picture for me to work with. Because what we would then create is a field here and 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 a field there. And so basically every plate would give us two, with the exception of the end one where we only get one. So if you look in my picture, if I label my plates, I would call this plate 1, plate 2, plate 3, and plate 4. And how many capacitors do I have? And I'm trying to say you have 7. You have double minus 1. There would be 2 here. Maybe I'll circle in red. So I got 2 here. I got 2 here. I got, 2, 4, 6.
I think if you got rid of plate
I,
4.
Yeah, I'm sorry. My bad. To make it fair, I got to have 4 on the top also. And so the fourth one on the top would have a plus and a minus, I mean a plus here and a minus over here, and would make a field there. Now my drawing looks a little better. So there's a lot of hard stuff about this problem. So I hesitate to say this is the hardest, but I'm kind of leaning that way, is to recognize how many capacitors do you really have here. And so if I was trying to draw it in what we might draw it like a circuit, I have this. I have a battery here, and I have the first capacitor in parallel with the second capacitor, in parallel with the third capacitor, in parallel with the fourth capacitor. And
So you would have 7 capacitors basically.
Yeah, let me, yeah, so I won't draw all 7, but in my drawing, I would have 7. So if you go back to the problem, they didn't really tell us how many plates we had. They just said they had N of them. So I would have to say that I have N minus 1 capacitors. That's kind of the first conclusion, and a hard one at that, is to say, okay, how many capacitors do you have? And so it's n minus 1. So coming back to the question, now that we know we have n minus 1 capacitors, we know that they're air-filled, we know that they're parallel plates, we could say this much. Give me something to write down, that the capacitance total would be C1, plus C2 plus C3, ... They're all identical. And so they would be n minus 1 times the capacitance of the first one. Okay. And so that's like I said, kind of the biggest step in it, but I don't know, we've got some more tough stuff to do.
Do we
That's
have
really,
to, is it going to lead up to having to do the Taylor series?
no, I don't think so.
Yes.
No. So I
Okay.
just have a bunch of capacitors, but they're all in parallel and they all have the same amount. So it's just n minus 1 times the capacitance of the first one. So let me then kind of look at the first one. The first one, if I tried to draw it, I would have a semicircle that looked like this. And maybe I'll try to draw the overlapping semicircle. Close. There. But what I want to get at is to say then this, which I'm coloring in red, would be the overlap area. And that's the part that has to do with C1.
Okay.
So I would say I have n minus 1, and then a parallel plate capacitor, and an air-filled parallel plate would have epsilon naught, the area overlap. And I want to be a little careful here because usually we write this as a D for the distance between them. But
Because it's parallel?
watch this. You come back to the picture. And maybe I need to make it a little bigger here for a second. What they call D in the problem is not the distance between a positive and negative plate. It's the distance between two plates on the bottom circle.
So like two positives or two negatives?
Right. So the distance between, if I come back over to this picture where I had the 4 going on, then I would say back here, the distance between them should be written as a D divided by 2.
Why is it divided by 2?
Okay, again, normally you write the capacitance to say this is the D, the distance between a positive and a negative plate.
Oh, okay.
But what they've done is they've given you a D that is not that D.
Okay, it's just, so because it's between two positives,
Mhm.
that's why we put it over 2.
Yeah, so again, coming back to here, they're saying in this problem, right? I can expand it again.
So if it's between the same charge, whether it's positive or negative, we put d over 2 in the equation.
Yes.
Okay.
See, right here, maybe I'll mark it in red. It says the distance right there, D, is from the neighboring plates, both connected on the same side there, both positive or both negative, depending on how they hooked it up.
Okay.
So when I come down here to do this calculation for the capacitance of a parallel plate, this is where I get to use that phrase again. You don't want to ever just plug and chug. You don't want to have an equation that has a D in it, and then you have a problem that has a D in it, and you go, oh, that's the same number. No, they just used the same symbol. And so the D that they're giving me in the problem is not the same as the meaning of that D in that equation. Now, they are related, and that's what I got to figure out. I got to figure out that it would be half of the distance.
Okay.
So that's a big step too. And now, of course, the other thing is how to figure out the equation for the area of this, what I colored in red. I'll circle it in red. This little pie-shaped thing, or pie or pizza. I like pizza a lot more than I like pie, so I like to call it a pizza slice there instead of a pie slice. Okay. But let's take a minor break from the physics and look at some math for a moment. So if I were to take a circle and cut it so that it has is this a section or a segment? I always get those confused.
I think that's a segment, right?
No, I don't, but anyways, I think it's a sector.
Yeah, sector sounds familiar.
Yeah, I think it's a sector, because you do that same thing with hard drives and writing the sectors of the disk. So anyways, whether I got the name right, I'll let Hunter look it up here while I'm working. But you know that the area of a full circle
It's a segment.
is pi r squared. What is it, Hunter?
It's a segment.
Segment.
A circle bounded by two edges is a segment.
Segment, okay.
Mhm.
All right, so this is a full circle, pi r squared.
Yep.
And if you wanted to know the area of this pizza piece right here, or this pie piece, and you called that theta, then you would only have a fraction. And if you did it in radians, you would call it theta over 2 pi. Since 2 pi is a full circle, so this is the area of a full circle right here, and then this is the fraction. However, here's where I want to be careful again, because I was just trying to show you some math. Let's come back and look at our picture, because your author's picture of theta is not what I drew.
It's that weird, like,
Okay,
weird.
good. I was going to try
Kinda.
trying to get it bigger, but it wouldn't get bigger. Okay, so coming back to this picture that I tried to draw here, and I'll try it again. This is what your author calls theta. So that means this angle here that's part of the pizza piece would be 180 minus, oh, let me do it in radians, would be pi minus theta.
The red part
The red part.
would be
Mhm.
that?
Yeah,
Okay.
right. The red part would be pi minus theta. So I'm going to go back to our math discussion and say, okay, so that means I need to modify this equation that I kind of did for you in math and write it not as theta over 2 pi, but pi
Minus
minus
theta.
over 2 pi times pi times r squared. So that would be the overlap area. And I didn't put area here, but maybe I should spell it out. Area. Okay, so let's use that back up here. And I'll pull it down here, but if I put all that together, it looks like I've got capacitance total equals. And yeah, I just wanted to check. So it's n minus 1. So this would be an n minus 1. Then it's an epsilon naught. Now the area, I'll put way over here. This would be pi minus theta over a 2 pi over a pi r squared. So there's the area. And the distance I'll put here. This is, well, I was going to do something and simplify it, but I'll do that on the next step. And so that's a d over 2. D over 2, yeah. Okay. Because a lot of this does simplify.
Yeah, you can cancel out the 2's and the pi's, it looks like.
Yeah, that might be it, huh? So this would be an n minus 1. Then I'd have an epsilon naught. Then I'd have the quantity pi minus theta and r squared all over d. That might be as far as we could get. I'm going to jump over to the solutions. And this was number 6.
Yeah, they have a 2 and but besides that, everything else.
I said it in words. I'm my deepest apology. Let's go back. Yeah, I said it in words, but I didn't write it down correctly. Sorry. Remember way back here when we did these 4 things, and I said you double it, take away 1.
Oh,
I didn't actually double it in my equation. I just put n minus 1. So I should have said at the very beginning 2n, and then that would have carried all the way down to here, 2n, and yeah, so good. So sorry about
Okay.
messing that up. I'm glad we checked the answers though. It's easy to do something simple.
that's all good.
Yeah. So,
Cool. That, yeah,
yeah, that's a tough one.
yeah, I was looking at it and just not really understanding what they meant when they were asking this stuff. So
Mhm.
I definitely need to go try that problem again, see if I can do it.
Yeah, and I would say that one in 47, I don't know if you've tried 47 yet, it's further down on the list, but you know, the first big step is to recognize that when you stack metal plates like this, you're making kind of like back-to-back capacitors.
Mm.
And that's how you make it mechanically. But on a circuit board, you would just say, hey, they're all in parallel with each other. Yeah. And so I don't know if you were paying any attention when I did the one with Anthony at 47, but I think that one had, at the end of it, it had, well, I can't remember, but it was just, it's the same idea that you have to recognize.
Yeah, I was working on another problem, but I'm gonna, if I struggle with that one, go back and watch a video on it and see.
All right. Good, good. And I'll stop that one. Let's see. That was number 6. Good. Oh, and then Jonah. Is Jonah still around? Oh, good. I see his crystal that from I think he said the New York Museum. It's a fascinating
Yes, you remember.
Yes. All right. So I got a 121 question after Daniel. All right. So fire away.
It's a 2D acceleration and velocity vector one. I'll share it.
Oh, good. Yeah, share it with me. Did I turn off my sharing so you can share?
Yeah.
Nice. Okay. So let's see if I can read this. It says at time equals to 0, an insect is flying with a velocity vector given with the following. Oh, and that, so Vx initial, oh, if I can expand that. Is that 3.98?
3.98. Oh yeah, I can zoom in.
Yeah. Meters per second and an initial velocity, oh, thank you, of 0. Okay. The insect then accelerates with a velocity vector given the following components. Okay, so the x component is 0.952, and we'll make a little note, insect problem for 121. Okay, and with a y component of 2.0 meters per second squared after a time t, the insect has a velocity vector, ooh, I like this, that makes an angle of 30 degrees. So the velocity vector is 30 degrees to the x-axis.
And
Wow.
my
I have to go. Hope everyone has a good weekend.
All right,
you too.
take care. Yeah.
I have a
Okay.
problem with graphing these vector problems with acceleration and velocity because I'm not sure how to graph. I can like graph velocity, but like once you add acceleration to it, I get messed up on how to graph them.
Yeah, well, okay, and I would even say this is two-dimensional, and I'm not sure making a graph, although I am going to make a picture, so I don't want to confuse you. I'm not sure graph's the way to go with this.
Okay.
Yeah. So after a time t, so let me just get to the question. The question is define t, is that it?
Yes.
All right,
Yeah.
because find t. All right, so, okay, so let me try this. I'm going to share my screen, so I'll bump you off. And then come over to here. Okay. And so let me just put here 121 insect problem. But let me do this first of all. I would say that instead of making a graph, I'm going to make a vector picture. Here's what I mean by that. When this one starts, okay, it says it has a velocity in the x direction only. So that would be a picture of the initial velocity, okay?
Mm-hmm.
Then if you look at the acceleration, there's an acceleration in the X and an acceleration in the Y. So what's going to happen after time, and maybe I'll just make another grid right below it so it doesn't fall on top of it and confuse you. The velocity in the X direction is getting bigger, so I'll draw a bigger one, but the velocity in the Y direction is also growing. And so you're going to get a final velocity, and then that's the question, when is that 30 degrees?
Right.
Okay. So here's where I would stop drawing pictures and now start doing some math. Let me move this one up, because I would say then the tangents of 30 degrees would be the final velocity in the Y direction over the final velocity in the X direction. And I'll come back up to the picture above it. This is the final velocity in the X here. And this is the final velocity in the Y.
Okay, and just to see if I understand this, so they gave me the VI in X and Y, and they gave me the VF, or they gave me the acceleration final in the X and Y.
Right.
Okay.
And
I need to use both of those to find the VF in both directions.
right. So then I would write the initial in the Y plus the acceleration in the Y over T. And then down here, I would write the initial in the X plus the acceleration in the X over T. And I'm kind of curious what the answer comes out. Sounds like you might have be okay on your own here, but if you'll bear with me.
Yeah, no, I will, but so that equation, what you got, the V naught plus, or V naught Y plus A final T. Where did you get that from? Oh, that's from last week's notes.
Oh, yeah, you're right. Okay, so yeah, let me emphasize the last week when you guys did one-dimensional motion, you saw that equation. And one of the lessons of this week when you're doing 2 dimensions is that you can take 2 dimensions and break it down into X and Y and then just treat them as one-dimensional motion. So I've done the numerator as one-dimensional motion in the Y, and I've done the denominator as one-dimensional motion in the X.
Okay, I see now. Yeah, I see it in last week's notes right here. V naught X plus AXT.
Yeah, so I put in the acceleration X and I put in the T. And then the initial velocity in the X direction was the 3.98. And the acceleration was the 0.952 T. And I'm going to just grab my calculator and say the tangent of 30 degrees, get a decimal to work with, is 0.577. And so now, on the right-hand side, I've got 2t. And on the left-hand side, I'll just write it out before I do the distributive. This would be 3.98 plus 0.952t. When I do the distributive property, the 0.577 times 3.98 is 2.30. And then the 0.577 times 0.952 is I'll just do 5 t. And then 2 minus that would be 1.45 t. Over here would be 2.30. And so 2.3 divided by 145 is a time of 1.59 seconds.
Okay.
Yeah, nice.
Yes, that's not a hard one.
Okay, good. But you know what was really hard about it, I think, it's just kind of, it's not kind of your standard straightforward, hey, just do X and Y. It's right back here realizing that when the problem gave you 30 degrees, there's a connection between X and Y.
Yes, I see that
And
connection.
that's
now.
connected with time, and that's the biggie right there, yeah.
Yeah, I didn't think to go back to the equation we used in last lecture's notes, but I should, because it's one dimension, same thing, just twice in this chapter.
Yeah, I kind of like to describe 2 dimensions. I said 2 dimensions is really 1 dimension twice.
All right, well, thank you.
Oh, my pleasure. All right, let's see. I'll stop that sharing when that was Jonah. Oh, so Jonah's the last one in the chat room. Any of you guys have one, or are you just kind of soaking it all in, kind of?
Doing my best to try to soak it all in. I tutor till 2 on Fridays, so this is like the last session I can get to. So
Okay.
Honestly, I'm just really trying to, what was that?
I was gonna say, in your case, you're probably best served by once I get these videos loaded and you can kind of scan them.
Yeah, no, I try to spend most of my weekend going over them and stuff like that. Honestly, just coming to these and kind of reviewing really helps me not get turned around in homework, because I find like the hardest part about doing them is obviously reading the math.
It is, yeah.
So
that's why I like that phrase so much.
yeah, no, I heard a couple people have gotten that tattooed before.
Yeah. That was, I had a group. That was interesting. Yeah, and well, not only they get a tattoo, but it was creative. I'll have to share a picture with you sometime. But they took Greek letters and modified them, and it was very artistic.
Mike, are you trying to sell me on a tattoo?
No. I actually, no, I'm not. I'm not at all.
For sure. Yeah. But honestly, I'm really loving the material we've been going over. I'm just like trying to keep up with it, like in a lot of units right now. So it's a juggling act right now. So
good.
But the one question I might have is, and I don't know if you have it figured out yet, is like what we should expect out of like the format for tests and stuff like that.
Oh yeah, let me double check. Because you're 122.
Yeah.
And your test is 11 days away.
The 29th, right?
Yeah, 29th, right? And on Sunday, actually for both of my classes, but for Sunday and particularly for you guys, I'm going to send out more information about the test. And one of the things that I think will serve you really well is that I've recorded about 3 years ago. I do this all the time, of course, in a face-to-face setting. I say, okay, right before the test, why don't we just all get together on a Sunday afternoon, and I'll just pick some problems from past tests that I've given, and I'll just go over them.
Okay.
And that's really helpful. And so my tests usually have 5 questions, and I think I picked like
5 questions.
10.
That's it.
Yeah, that's it, right?
Right.
Just 5. So it's like 25 minutes problem. You really can't do more than that. You know how long these are taking.
Oh yeah, no, for sure.
Yeah. But I think watching the video, you'll feel really comfortable because you'll see the problem, and I'll just say, okay, here it is. And what you should do is practice being able to do a problem like this in 25 minutes.
Okay. So kind of just being able to like review those, see like what I should be able to kind of analyze, digest, and then spit out an answer for.
Yeah, yeah. And so if you, in theory, if you do all the homework and
Mhm.
you start to get, because at first the homework's going to take you, a problem's going to take you a long time. But
Mhm.
by the end of the homework, hopefully you are getting more solid on it to the point that, oh, I can read the problem, I can then try the problem, and yeah, I may have a couple of false starts, but I can get it done within 25 minutes. And that's really where you want to be for the test. So without practicing a lot of these, you will run out of time in a test. But if
Okay.
you've done all the homework, and some people actually, after doing the homework, probably still need to do some more practice ones because they're not quite ready.
Mhm.
Most people need to do the whole homework assignment before they're ready. Some people actually could probably do half the homework assignment and still say, oh yeah, I got the general idea. You give me any problem now, I can figure it out on capacitors. Because
I think I definitely need to still do some more practice.
so I like to tell people, just start practicing problems. First of all, do all the homework. And then second of all, do these practice ones that I'm going to send out. I'm going to give you about 10 of them.
Okay.
And I would even encourage you to do them first and then watch my review of those problems.
Okay, yeah, give them a shot first. Yeah, I've been trying to go ahead and do all the like at least give all the problems a little bit of a shot before I go and do the solutions too. So
yeah, and
awesome.
then also, and then for you guys, since give you a little heads up, you could even do one more thing because since all the video recordings are already out there, if you look ahead one or two recordings, you'll see that after I had given that class the test and passed it back, I went over it in class. So you can actually see, yeah, the test I gave them and the problems I went over. So you'll have that advantage too to say, hey, so I'll try to find that one and put that in my Sunday update and say, okay, as you practice getting ready for the test, look ahead into a couple of weeks where I actually finally got the tests all graded and passed back to the students. And you'll see that I cut out the first hour of class and just went over the test. And then it'd be good for you to see it before you take the test, or the first test.
Yeah, agreed. Awesome. Cool. Yeah, I think I just need to really kind of just practice it all. So yeah, I don't really have much else, but thank you so much for all the insight and
Okay. You bet.
go over the problems.
All right. Oh, hey, good. You're asking me another question about 121 test, huh? Yeah, well, I know his tests are probably different than mine, and I'm not even sure how they are. But I will say this, I do have a universal answer that I think will work. And that's practice these. I would encourage you, he's given you some good problems through his computer system. But I could be wrong here, but I almost feel like maybe you might be spending too much time working on his computer system and not enough time practicing the problems. And I would say, let me find it for you. Practicing, doing the test. What am I trying to say? Doing the test review that I gave would probably also be very useful. I guess that's what I'm trying to say. My test, I'm not really sure how Professor Folsom's going to do his test, but why not, you should ask him and I'll see what I can do to help you guys, because I think he dramatically changed it from the traditional way. The traditional way has been, do a couple of chapters and then take the test, but he's doing like a quiz for each one at the end of each chapter. And if you want to go ahead and look at my lectures, I think Professor Folsom has given you the links to my lectures for 121. And so watching me do some of those examples, I think is really good. But also, I have test reviews there. Now, if I think for 121, it wasn't me who did the test reviews and recorded it. You'll see another guy called Don Ian. He's since retired. But he took a bunch of my old tests and just made problems and told the students to come in on a Sunday and say, all right, come on Sunday and we'll just do a bunch of these. But if you go to the same YouTube channel, I think it's called SBCC Physics on YouTube, and you look at all those playlists, besides a playlist for your class 121, and the class I'm teaching 122, and another class we teach in the spring 123, those are kind of the big playlists. But there's also a playlist for the test reviews. And the test reviews are, all of them are just either myself or my assistant Don taking problems from my old exam and kind of running through them. And I think that would still work. I am a big fan of the universal idea of practice these problems, because even though Doug may not be taking the problems out of the book or ones close to them out of the book like I've done, he's still kind of making them up with the idea that, hey, there's a connection between velocity and the x and velocity and the y, like that problem I just did, the 30 degrees. And those kind of problems show up in the book. Yeah. And so that's probably the best I can give. It's because I'm not real sure how your testing and your quizzes go. It's certainly not the traditional way, and that's kind of my thinking. Hope that helps. Okay, good answer. Thanks. All right, have a good week. And all right, take care. Yep. We'll learn more and more as this goes along, and I think our Fridays will get better and better. All right. Oh, wow, it's 4:30. All right, Jonah, unless you have a question, I'll check out here and stretch my legs again. And you have a good weekend too. And keep shooting questions at me. Take care.